we will move or proceed further with the next topic, that is nothing but topological ordering. This is also part of the graph itself. Now, sometimes some textbooks or some authors call it as topological sorting or topological sort. But anyway, topological ordering or topological sorting is same. There's no difference between them. They are both same. Now, let us first look at, don't worry, this is not sorting of vertices or, I mean, it's like a sorting of vertices, but not sorting of elements or something like merge sort or quick sort that we have to uh, have a lengthy procedure. It's very simple. What topological ordering or topological sort says that topological order means for a directed graph, there is an ordering of vertices like V1, V2, V3, since till n number of vertices, such that every vertex Vi comma Vj, this that is Vi is one vertex and Vj is one vertex. So for every Vi and every Vj vertex, its edge, that is edge between Vi and Vj. For that, the vertex I should be less than vertex j. Vertex I should be less than vertex j. Now, looking at the definition, this is a little confusing, but let us proceed and try to solve try to look at what topological sort is. Now, what actually topological sort means is, if we look at this graph, we have certain number of vertices here, n number of vertices. We have vertex A and vertex B. Is there an edge between vertex A and vertex B? There is no edge. So these two vertices are actually at one level. Now let us examine another pair of vertex, Vi and Vj. Vertex A and vertex C. Is there an edge between vertex A and vertex C? Yes, there is an edge. Now that edge is directed. Remember, it is directed. Now obviously directed edge means it has orientation. So what we are saying here is, when we have an edge between vertex A and vertex C, vertex A is coming before vertex C. So that is what? I is less than j. So A is before C. So we will have a series A comma C, ordering of vertices A comma C. Then what about B and C? Is B before C or B is after C? It doesn't matter because there is no edge between B and C. What about A and B? It doesn't matter. A is before B or B is before A. It doesn't matter. Why? Because there is no edge between A and B. But suppose if there would have been an edge, then we would have been able to say that which comes first, A comes first or B comes first. And in the same way, if we look at A and E, is there a direct edge? No, there is no direct edge between A and E. Then can we say A is before E in the ordering? Because A comma E, there is no edge from A to E. But will A be before E or will A be after E? A will be before E always. Why? Because there is an edge between A to C, then C to E. So actually what is happening here is, there is no edge between A to C, but in ordering we say that A to C, so A is before C, so we write A comma C. Then C is before E, so we write C comma E. So it's nothing but A comma C comma E. That is how we try to figure it out or find out the order. Now for this complete graph, let us look at the ordering of vertices or topological order. Now initially, we will be taking help of a stack to perform this operation. And this stack will be empty initially. The first thing what we do is for every vertex, we try to compute its in degree. So in degree means the edge which is coming into the node or vertex. So for A, there is no edge coming in, so its in degree is 0. For B, its in degree is 0. For C, its in degree is 1 because there is one edge coming. Now remember here I have used boxes. The first, the left hand side, the right side of the box represents the in degree, and the left hand side of the box we will try to represent the label of the node, which ordering it has. So we will try to order it according 1, 2, 3, 4 that way. So left side is ordering and right side is in degree. So in degree of, I have put up question mark because right now we don't know what is their ordering. So 0 for A, in degree is 0 for B, in degree is 1 for C, in degree is 3 for D because there are 3 incoming edges. For F, in degree is 2. For G, in degree is 2. For E, in degree is only 1 because there is only one edge coming. And for H, in degree is 3. And rest of the question mark says that there is no ordering yet. So for every vertex, we have computed the in degree. And if the in degree is 0, we push that vertex onto the stack. We will push that onto the stack. So initially stack will be empty, so A and B will not be there. And then in degree of A is 0, in degree B is 0. Now I can push A first, then again push B, doesn't matter. Or I can push B first and push A next, doesn't matter. So you can start anyway, it doesn't matter. Now, why I have pushed B first and then A, because I'm trying to follow the same method what the textbook has followed. So that we don't have any confusion there. But remember one thing, for a given graph, there can be many topological orderings. The only thing is, whenever you select an edge between two vertices, vertex Vi should I should be less than vertex J. That is Vj. I should be less than J. So let us come back to this part. So I have pushed B first, then pushed A. Then while stack is not empty, we will pop out. So once we perform pop operation, A gets popped out. So A is popped out from the stack. And here I am trying to label the vertex A as 1. So initially we are starting from labeling as 1. And the edges, what I have made is dotted. That means they are explored, it's done. Then for each outgoing edge from vertex, so from A, outgoing edges to C and to D, decrement the in degree of incident vertex. So here in degree of C was 1, if you remember. In the previous slide, I'm just going back. In degree is 1, and for D, in degree is 2. Rest in degree doesn't matter, 0, 2, 2, 1 and 3 respectively doesn't matter. So 1 for C, in degree 1 for C has become 0 because we have decremented it. Then for D it was 3, it has become 2. Rest of the in degrees doesn't matter, doesn't change, because those are not the outgoing edges from the vertex. So we labeled the vertex and we decrement the in degree, because that edge we say is gone. Now once we decrement it, is there any vertex whose in degree is 0? If there is any vertex which in degree is 0, we will push that onto the stack. So in this case, C's in degree has become 0. So we will be pushing C onto the stack. We have already labeled A as 1. We push C onto the stack. Then again, stack is not empty. While stack is not empty, we pop out C. Now from C, there is an edge to D to E and H. Now C, we will label it as 2 because A was labeled as 1. We increment the label counter also. I mean, though it's not, I have not written as a statement here, we increment the label counter, it becomes 2. So this has become 2, and then the label of C has become 2. Then in degree of D was 2, has decremented to 1. E, it was 1, it has become 0. H, it was 3, it has become 2. Rest of the in degrees doesn't change because the edges are not incident. Now, is there any vertex whose in degree has become 0? D is there, 0, it's 1. E is 0. So we push E onto the stack. Then again, stack is not empty. We pop out from stack. It's E which gets popped out. So E, once it pops out, it's labeled as 3. That is the third vertex in the ordering. So A comes first, C comes for second, then E comes. From E, there is an H to G. So G's in degree was 2, it has become 1. Now, is there any node whose in degree has become 0? No. So leave it as it is. Then what is left out? B was there in the stack. Then again we perform pop operation. So B gets popped out. Don't worry about D. This is actually should have been hidden here. But B is there. B gets popped out. B's label is 4 now because E was 3. B's label will be 4 because B is popped out. Then the edges from B, that is going to D. So D's in degree will decrement. It becomes 0. F was 2. It becomes 1. Then D is in degree 0. So D gets pushed onto the stack. Then D gets popped out. So because and gets labeled as 5 because that's the next level from 4, 5. And D has an edge to F. So F becomes 0 and F is pushed. Then again we perform pop operation. So F gets popped out and it is labeled as 6, and F has G as the edge from F to G makes G as 0 in degree. So G is pushed on the stack. H in degree was 2, it becomes 1. It's decremented. Then G gets popped out and gets labeled as 7, and H in degree becomes 0. So when H becomes 0, H is pushed onto the stack. When H is pushed on the stack, last thing is stack is not empty, we pop out H. So once we popped out H, we label H as 8 because after 7, the next label is 8. And then there are no more vertices to be visited. So we have the topological ordering as A, C, E because we have to now follow the labels which we have given for each vertex. So A is 1, A, C, E, then B, that is what I have, B, D, F, G, and H. This is the topological ordering for this graph. Now remember, this is one sequence of topological ordering. If we would have inserted A first or pushed A first then B, then we would have got a different topological ordering. So it doesn't matter. A graph may have different topological ordering, but the only thing which we have to remember is for each edge from Vi to Vj, I should be less than j to get the ordering for every vertex and every edge. So this is what is topological ordering, and we try to take help of stack to perform this operation. Now let us look at the algorithm. So this algorithm is topological sort. Initially we have the obviously G is a digraph, it's a directed graph. That's the input we give. S is the empty stack, initially empty. For all vertices, for every vertex U, we compute its in degree and store it in some array. It's known as in counter over here. Then if the in degree is 0 or in counter value is 0, then we push it onto the stack. I is used for the label. I told you label gets incremented. So initially the label is 1. It's not assigned to anything. So I is the label there. When stack is not empty, we pop out whatever vertex we have popped out. That vertex is the ith vertex. So it is labeled as I. So we started from 1, then labeled as 2, 3. So that's what we have. We should be incrementing. So I gets incremented for the next to label the next time. Then for each edge, which is an outgoing edge, for any vertex W, we decrement its counter. In counter is nothing but which has been storing in degree. So we decrement the encounter. And if the in degree becomes 0, we push it onto the stack. And then once the I is greater than, and because at last what happens is, in our case we had 8 vertices, so then again incrementing 8, it becomes 9. So 9 is greater than n, then that means we have a topological ordering. Otherwise what happens is I will not get incremented because there will be a cycle in the graph. So when there is a cycle in the directed graph, then we will not be able to find the topological order. So we return the series or sequence of vertices, or we try to, we say that there is a cycle. So there will not be any topological ordering, because one cycle is there, all the I is greater, I is less than j means, I mean, we will be roaming around the entire graph. Will not get any solution there. So that is what is all about topological ordering.